Welcome! In this session, we'll dive into problem number 1853, convert the temperature. This problem challenges us to convert temperature values from Celsius to both Kelvin and Fahrenheit using mathematical formulas. Let's explore the solution step by step, discuss different approaches, and analyze their complexities. Let's get started. In this problem, we are tasked with writing a function that converts a given temperature in degrees Celsius into both Kelvin and Fahrenheit. The conversion formulas are straightforward. To calculate Kelvin, we simply add 273.15 to the Celsius value, and to calculate Fahrenheit, we multiply the Celsius value by 1.80 and then add 32.00. The function should return these two results in an array, where the first element represents the temperature in Kelvin and the second element represents the temperature in Fahrenheit. For the input format, we will receive a single floating point number representing the Celsius temperature. The output, in turn, will be a list containing two floating point numbers, the first being the Kelvin temperature and the second being the Fahrenheit temperature. Now, let's look at some examples to reinforce the concept. For the first example, we have an input of 36.50 degrees Celsius. Using the formulas, we calculate Kelvin by adding 273.15 to 36.50, which gives us 309.65. For Fahrenheit, we multiply 36.50 by 1.80 and then add 32.00, resulting in 97.70. This means the output for this input is the array 309.65, 97.70, where the first value corresponds to Kelvin and the second to Fahrenheit. This demonstrates how the function applies the formulas step by step to produce the expected result. For the second example, the input is 122.11 degrees Celsius. To find the Kelvin equivalent, we add 273.15 to 122.11, which yields 395.26. For Fahrenheit, we multiply 122.11 by 1.80 and add 32.00, resulting in 251.80. The output here is 395.26, 251.80. Additionally, note the constraints provided for this problem. The Celsius input can range from -1000 to 1000, and the function should ensure the output values are rounded to two decimal places. Moreover, you don't need to worry about invalid inputs, as the problem guarantees that the input will always be a valid floating point number. Finally, let's consider some edge cases. For extreme negative Celsius values, such as -273.15, which represents absolute zero, Kelvin becomes 0.00, and Fahrenheit is calculated as -459.67. For large positive values, like 1000.00, Kelvin becomes 1273.15, and Fahrenheit is 1832.00. Another key edge case is when the input is 0.00, the freezing point of water. In this scenario, Kelvin is 273.15, and Fahrenheit is 32.00. These examples highlight how the function handles a variety of inputs, ensuring accurate results across the entire valid range of Celsius values. To solve this problem, we first considered the brute force approach, which involves directly applying the given mathematical formulas for temperature conversion. Specifically, the Kelvin temperature can be calculated by adding 273.15 to the input Celsius value, and the Fahrenheit temperature can be derived using the formula Celsius multiplied by 1.80, then adding 32.00. This approach is straightforward because it only requires basic arithmetic operations, addition and multiplication, making it computationally efficient. With no loops, recursion, or complex data structures involved, the time complexity is O1, and the space complexity is also O1. This means the solution is both fast and memory efficient. Additionally, we briefly considered an alternative approach that involves pre-computation. In this strategy, we would store Kelvin and Fahrenheit equivalents for a predefined range of Celsius values in a lookup table, which could potentially save computation time during repeated queries. However, this method introduces unnecessary complexity, which we'll discuss further. The pre-computation method, while conceptually interesting, has significant drawbacks. It requires additional memory to store the lookup table, resulting in a space complexity of O(n), where n represents the range of Celsius values being pre-computed. This is inefficient for our current problem because there are no constraints or guarantees about the input range, and the lookup table could become unnecessarily large. Instead, the brute force approach is the most practical choice. The intuition behind selecting this method is rooted in its simplicity and efficiency. Since we are only converting a single Celsius value into its Kelvin and Fahrenheit equivalents, using the provided formulas directly is sufficient. The calculations are linear, requiring only a few basic arithmetic operations, and there's no need for iteration, recursion, or any advanced data structures. Furthermore, the computational requirements are minimal, as the input size is fixed to a single value, and the output is just a pair of numbers. These observations reinforce the idea that a direct calculation method is the optimal solution. When comparing approaches, the brute force method stands out due to its minimal computation and memory requirements. With a time complexity of O(1) and a space complexity of O(1), it achieves the desired results efficiently. On the other hand, the pre-computation method, while potentially useful for scenarios with repeated queries over a constrained input range, introduces a higher space complexity of O(n), without offering significant advantages for this specific problem, where the input range is unconstrained. Additionally, other numerical methods, such as leveraging external libraries or frameworks, would add unnecessary overhead and complexity to a problem that can be solved with a few simple arithmetic operations. Ultimately, the brute force approach was chosen because it directly applies the given formulas, producing the required output in constant time with no additional resource usage. Its simplicity, clarity, and efficiency make it the best solution for this problem, avoiding the pitfalls of over-engineering for a straightforward task. To solve the problem of converting a temperature from Celsius to Kelvin and Fahrenheit, we start by breaking it down step by step. First, the input is a single numerical value, C, which represents the temperature in Celsius. The goal is to calculate two outputs, K, the equivalent temperature in Kelvin, and F, the equivalent temperature in Fahrenheit. To accomplish this, we use two straightforward formulas, K equals C plus 273.15 and F equals C asterisk 1.80 plus 32.00. The first formula adds 273.15 to the Celsius temperature to convert it to the Kelvin scale, which starts at absolute zero. The second formula adjusts the Celsius value to align with the Fahrenheit scale by scaling and shifting it. The algorithm begins by taking in the input C, ensuring it is a valid number. For example, if C equals 25.0, this represents 25 degrees Celsius, which will be used in the subsequent calculations. Next, the Kelvin equivalent is calculated using the formula K equals C plus 273.15. This formula works because the Kelvin scale starts at minus 273.15 degrees Celsius, so adding 273.15 to any Celsius value translates it to the Kelvin scale. For example, if C equals 25.0, the calculation is 25.0 plus 273.15, resulting in K equals 298.15. Afterward, the Fahrenheit equivalent is computed with the formula F equals C asterisk 1.80 plus 32.00. The factor 1.80 adjusts the scale to Fahrenheit, while adding 32 shifts the 0 point. Using the same input, C equals 25.0, the calculation is 25.0 asterisk 1.80 plus 32.00, which simplifies to 45.0 plus 32.00, giving F equals 77.0. Once both values are computed, the algorithm returns or prints the results K and F. For the input C equals 25.0, the outputs would be Kelvin equals 298.15 and Fahrenheit equals 77.0. Now, let's consider edge cases to ensure the algorithm handles all valid inputs correctly. Negative temperatures, for instance, should work seamlessly. For example, if C equals -40.0, the Kelvin equivalent is -40.0 plus 273.15 equals 233.15, and the Fahrenheit equivalent is -40.0 asterisk 1.80 plus 32.00 is equal to -72.0 plus 32.00 equals -40.0. Notice that -40 degrees Celsius equals -40 degrees Fahrenheit, an interesting property of the two scales. For C equals 0.0, representing freezing point in Celsius, the outputs are K equals 273.15 and F equals 32.0. The algorithm is also robust enough to handle large values without precision loss. For instance, C equals 10⁻⁶ calculates Kelvin and Fahrenheit accurately, leveraging double precision arithmetic. The problem's simplicity ensures that it operates in constant time, 1, as the calculations involve only basic arithmetic operations with no loops or recursion. Precision plays a key role in this algorithm, especially when dealing with fractional inputs like C equals 36.6. Floating point arithmetic ensures accurate results even for such values. Additionally, extreme inputs, such as very large or very small values like C equals -273.15, are handled effectively without losing precision, thanks to the robustness of floating point operations. Scalability is another strength of this approach. While the problem itself is straightforward, it can be extended to process batches of temperatures efficiently. Since each conversion is independent, there are no shared states, making the process highly parallelizable. For input storage, the temperature in Celsius, C, is represented as a floating point number. Similarly, the outputs K and F are also stored as floating point numbers to ensure that fractional temperatures are handled accurately. Finally, the simplicity of the problem means no additional data structures are required. Since the algorithm performs direct calculations, structures like arrays or hash maps aren't necessary. Each computation is lightweight and efficient, making the algorithm suitable even for constrained environments. Optimizations include avoiding redundant calculations by ensuring Kelvin and Fahrenheit are computed independently and directly. For systems with relaxed precision requirements, single precision floating point arithmetic can be employed to reduce memory usage, particularly in embedded systems. Additionally, for advanced use cases, a batch processing approach can be implemented. This leverages vectorized operations, such as those provided by libraries like NumPy and Python, to convert multiple temperatures at once, further enhancing efficiency. This combination of simplicity, precision, and scalability makes the algorithm both elegant and practical. The provided Python implementation solves LeetCode problem number 1853, convert the temperature. The task is to convert a given temperature in Celsius to both Kelvin and Fahrenheit using the specified formulas. Here's a detailed explanation of the code. 1. Class and function setup. The solution is encapsulated in a class named solution with a method convert temperature. This is the standard format for LeetCode problems. 2. Input parameter. The function takes one argument, Celsius, which represents the temperature in Celsius to be converted. 3. Conversion to Kelvin. The Kelvin temperature is calculated using the formula Kelvin equals Celsius plus 273.15. This formula shifts the Celsius scale to the Kelvin scale by adding 273.15. The result is stored in the variable Kelvin. 4. Conversion to Fahrenheit. The Fahrenheit temperature is calculated using the formula Fahrenheit equals Celsius asterisk 1.80 plus 32.00. This formula first scales the Celsius temperature by a factor of 1.80 and then adds 32 to adjust for the Fahrenheit scale. The result is stored in the variable Fahrenheit. 5. Returning the results. The function returns a list containing both the Kelvin and Fahrenheit values in that order, Kelvin, Fahrenheit. This matches the expected output format described in the problem. 6. Efficiency. The solution performs simple arithmetic operations, making it very efficient with constant time complexity 1. This implementation is concise, accurate, and adheres to the requirements of the problem. It handles all valid inputs for Celsius and ensures correct conversions using the given formulas. This is the Java implementation of the LeetCode problem, convert the temperature, number 1853. The functionality mirrors the provided Python implementation. The method convert temperature takes a double input representing the temperature in Celsius, converts it to Kelvin and Fahrenheit, and returns the results as a double array. Key differences include explicit type declarations for variables, the use of Java-specific syntax for arrays, and the absence of Python-specific features. This ensures the solution is idiomatic to Java while maintaining the same logic. To start, we are tasked with converting a temperature of 25 degrees Celsius into both Kelvin and Fahrenheit. The first step is to calculate the equivalent temperature in Kelvin. Using the formula for Kelvin, which is Kelvin equals Celsius plus 273.15, we substitute the given value of 25 degrees Celsius. Adding 25 to 273.15 gives us a result of 298.15 Kelvin. This is the first part of our solution. Next, we calculate the equivalent temperature in Fahrenheit. The formula we use here is Fahrenheit equals Celsius asterisk 1.80 plus 32.00. Substituting the value of 25 degrees Celsius, we first multiply 25 by 1.80, which equals 45.00. Then, we add 32.00 to 45.00, resulting in 77.00 degrees Fahrenheit. Finally, the function returns both results as a list, 298.15 for Kelvin and 77.00 for Fahrenheit. Now, let's take another example where the input temperature is 0 degrees Celsius. We begin by calculating the temperature in Kelvin. Using the same formula, Kelvin equals Celsius plus 273.15, we substitute 0 for Celsius. Adding 0 to 273.15 gives us 273.15 Kelvin. This completes the Kelvin conversion for this input. For the Fahrenheit conversion, we again use the formula Fahrenheit equals Celsius asterisk 1.80 plus 32.00. Substituting 0 degrees Celsius, we first multiply 0 by 1.80, resulting in 0.00. Then, we add 32.00 to 0.00, which gives us 32.00 degrees Fahrenheit. The function then returns the results as a list, 273.15 for Kelvin and 32.00 for Fahrenheit. In our third example, we are converting minus 40 degrees Celsius to both Kelvin and Fahrenheit. Starting with Kelvin, we use the formula Kelvin equals Celsius plus 273.15. Substituting minus 40 for Celsius, we add minus 40 to 273.15, resulting in 233.15 Kelvin. This is the Kelvin equivalent for this input. Finally, we calculate the Fahrenheit equivalent for minus 40 degrees Celsius. Using the formula Fahrenheit equals Celsius asterisk 1.80 plus 32.00, we substitute minus 40 for Celsius. First, we multiply minus 40 by 1.80, which gives minus 72.00. Then, we add 32.00 to minus 72.00, resulting in minus 40.00 degrees Fahrenheit. The function returns the results as a list, 233.15 for Kelvin and minus 40.00 for Fahrenheit, completing our solution for this example. Here, we analyze the time complexity of the convert temperature function. The time complexity is O(1), because the function performs a constant number of operations, regardless of the input value. Specifically, it calculates the Kelvin temperature by adding 273.15 to the input Celsius, computes the Fahrenheit temperature by multiplying Celsius by 1.80 and adding 32.00, and then creates a list containing these two results. Each of these steps is independent of the size or value of the input, meaning their execution time remains constant. Therefore, the overall time complexity of the function is O(1), as the number of operations does not increase with the input size. Now, let's look at the space complexity of the convert temperature function. The space complexity is also O(1), because the function uses a fixed amount of memory, regardless of the input. The input variable, Celsius, is a single floating point number, which occupies a constant amount of memory. Similarly, the intermediate variables, Kelvin and Fahrenheit, are also floating point numbers, each requiring a constant amount of memory. Finally, the function creates a list with exactly two elements to store the output, and since the size of this list is always fixed, it also contributes a constant memory usage. No additional data structures are created, and the memory usage does not grow with the input size. As a result, the overall space complexity is O(1). Additionally, since there are no iterative or recursive processes and no room for further optimization, this implementation is already the most efficient in terms of both time and space complexity. In terms of best, average, and worst-case scenarios, the function's time and space complexities remain consistent at O(1). This is because the function executes the same fixed sequence of operations regardless of the input. Whether the input is a small value, a large value, or any special case, the computations involve the same arithmetic operations and the creation of a two-element list. Mathematically, this can be expressed by summing the constant times for each operation, addition, multiplication, and list creation. The total execution time is a constant sum, which simplifies to O(1) in big O notation. Similarly, the memory usage is fixed and does not depend on the input size, confirming the space complexity as O(1). These characteristics make the function highly predictable and efficient under all circumstances. When working with temperature conversions, there are a few common mistakes to watch out for. One frequent error is using the wrong conversion formula. For example, when converting Celsius to Kelvin, some people forget to add 273.15 or use an approximate value like 273 instead of the precise 273.15. This might seem minor, but precision is crucial, especially in scientific or engineering scenarios, since even small deviations can lead to errors in subsequent calculations. Another issue is rounding values too early. For instance, truncating a Kelvin value to an integer before converting it to Fahrenheit can introduce compounded errors later in the process. Additionally, the Fahrenheit conversion formula is prone to missteps, such as misplacing parentheses or not respecting the correct order of operations. For example, writing Fahrenheit equals Celsius *9/5 plus 32 instead of Fahrenheit equals Celsius *9/5 plus 32 would yield incorrect results. These small mistakes can significantly impact the accuracy of your solution, so it's essential to stay vigilant when implementing these formulas. Now, let's explore some other areas where errors can creep in. Ignoring edge cases is a big one. For example, failing to test extremely low values like -273.15 degrees Celsius, which represents absolute zero, or very high values like 10⁻⁶ degrees C, can expose hidden bugs in your implementation. These edge cases challenge the robustness of your solution and are especially important in situations involving extreme input ranges. Another common pitfall is overlooking unit conversions in your code. Hard-coding constants without proper documentation or validation can create issues, especially if the problem requirements change or involve multiple systems of units. For instance, if your program assumes Celsius as the input but later needs to handle Fahrenheit, hard-coded constants might no longer apply. Being mindful of these factors ensures your solution is both flexible and robust, even in dynamic or complex scenarios. In an interview setting, there are some key strategies to keep in mind when tackling temperature conversion problems. First, always clarify the requirements. For instance, ask if precision matters and whether the interviewer expects rounded results or full decimal accuracy. This helps you tailor your approach to their expectations. Additionally, be aware of edge cases, such as handling -273.15 degrees Celsius, the lowest possible temperature, or other extreme values. Interviewers may also expand the problem to include conversions between Fahrenheit, Kelvin, and Celsius or introduce constraints like performance limits. If you're tasked with converting a list of temperatures, optimizing for multiple conversions becomes important. Techniques like pre-computing results or using vectorized operations can significantly improve runtime. Finally, if the discussion revolves around accuracy versus performance, take the opportunity to explain the trade-offs involved and justify your chosen approach. This demonstrates your ability to think critically and adapt to different scenarios. Temperature conversion problems are not limited to just one LeetCode question. For example, LeetCode 2469 focuses directly on temperature conversions, making it a good complementary exercise. Related problems like LeetCode 66+1 deal with precision handling and edge cases, while LeetCode 67, add binary, highlights numerical conversions. LeetCode 13, Roman to integer, explores the logical thinking required for conversions between systems, which can also apply here. Beyond related problems, there are alternative solution approaches to consider. A brute force approach involves directly applying the formulas for Kelvin and Fahrenheit conversions. This method is straightforward and accurate but may not scale well for large datasets or repeated conversions. For more efficiency, a vectorized approach using libraries like NumPy in Python allows for batch processing of conversions, making it ideal for handling large datasets. However, this method introduces additional dependencies and might be overkill for simpler use cases. Choosing the right approach depends on the specific requirements and constraints of the problem. Another alternative approach is to use a pre-computed lookup table. This method involves calculating and storing common conversions, such as Celsius to Kelvin, for a fixed range of values. With this table in place, you can retrieve results almost instantly, making it highly efficient for repeated queries. However, this approach has its trade-offs. It requires additional memory to store the table and is less flexible when dealing with arbitrary temperature ranges outside the pre-computed values. Despite these limitations, lookup tables can be a powerful tool in scenarios where speed is a top priority and the range of inputs is predictable. By understanding the advantages and trade-offs of each approach, you can select the one that best fits the problem's context and requirements. Great job! We've successfully solved problem number 1853, convert the temperature. By applying direct calculation formulas, we achieved an efficient solution with 1 complexity. Key takeaways include the importance of understanding mathematical conversions and handling edge cases. Thank you for joining. Don't forget to like, comment, and subscribe. See you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!